So far, we learned how to check whether a given graph, being it bipartite or not, has a perfect matching. But a more practical question is probably, what is a perfect matching there? So how do we find one when such exists? And this is the question that we'll answer right now. For technical simplicity, we'll consider only bipartite graphs, although what we'll design can be actually generalized to arbitrary graphs. As we learned, for bipartite graphs, a convenient way to connect matching existence to a matrix determinant is to consider an Edmonds matrix of a graph. So let's again take a matrix where the rows correspond to vertices of the upper part and the columns correspond to vertices of the lower part, and on the intersection of ith row and jth column we place for now a variable xij if the corresponding vertices are adjacent and 0 otherwise. So now to check that a graph has a perfect matching, we didn't compute a determinant in its whole generality, a determinant as a symbolic polynomial, but we rather replaced from the very beginning these xij's with just random numbers and then computed the determinant of a given numeric matrix. But now it's unclear when we get a determinant and it's not 0, we cannot back decompose a number, a determinant of this matrix, back into terms in the sum that define the determinant. So we know that each non-zero term corresponds to a matching in a graph, but these matchings are kind of glued together numerically as soon as we sum the terms up. And to be able to extract one specific perfect matching in a graph, we need for it somehow to be very unique. And how do we make a perfect matching a unique one? Well, we just add weights to the edges of the graph. And then, oftentimes, a minimal weight perfect matching or a maximal weight perfect matching might be unique. So this is exactly the idea which we'll now use. This idea is formalized in an isolating lemma. The lemma about isolation, about making something unique for a given problem of combinatorial optimization. This lemma, in general, deals with all combinatorial optimization problems that fit into discrete linear subset framework. So let's define what a discrete linear subset problem is. Suppose that we have an arbitrary finite set E, and we have a weight function, mapping E to, say, real numbers, non-negative ones. And suppose that we have a collection F of subsets of E. So mathematically, this is a subset of Boolean of E. So this guy is a collection of subsets of E, which we call good or feasible. So our goal is to find a feasible subset of E having minimal or maximal weight, where weight of a subset is just a sum of weights of elements belonging to the subset. Now we note that many problems about graphs can be stated in this framework. For instance, a problem of finding a shortest path between a pair of vertices. So if we are given two vertices S and T, we can just say that a feasible subset of edges of the graph is a subset of edges that joins S and T. And now we are searching for a minimal subset of edges that links S and T, where the weight of this subset of edges is just the sum of the weights of individual edges. The minimal spanning tree problem can be stated like this as well, as soon as we define feasible subsets to be spanning trees of the graph. So is for traveling salesman problem, for instance. So we can see that this is really a very general framework. This general framework is called discrete linear subset problem, or DLS problem. Discrete, well, because it's a problem of discrete optimization, we are to choose a subset of a finite set. Linear, because the weight of the subset is calculated as a sum of the individual weights, and so this is called a DLS problem. So now the question is, when does this problem have a unique solution? And isolating lemma gives a lower bound for the uniqueness of the solution to this problem. So let's assume that our weight function is random, so that for every element of the set E, its weight is taken at random, for instance from an element of weights from 1 to some number capital M. This actually is not that important, we just assume this for simplicity of notation currently. Then the lemma states that the probability of uniqueness of the solution of the DLS problem can be bounded from below by m minus 1 over m to the power of cardinality of E. So this implies that when the set from which we choose our weights at random is large, then the probability that there actually will exist only one solution to our DLS problem, this probability can be made pretty close to 1. So as soon as we prove this lemma, we'll apply it to our problem of perfect matching. We'll choose the weights of graph edges so that although original graph, unweighted graph, could have many perfect matchings, with high probability after we add weights to the edges, there would exist just one unique minimal weight perfect matching. And now let's switch to the proof of the isolating lemma. We'll consider that we are now having a minimization problem, and for maximization case, the proof is analogous. Let's calculate first the number of all weighting functions if we know that their values are in this set from 1 to m. The number of these weighting functions equals to the cardinality of the set of weights from which we are choosing to the power of the number of elements for which we need to choose the weights. And this is the number of all weighting functions. We'll now prove that the number of good weighting functions, that is the number of functions for which the solution to the DLS problem is unique, the number of such good weighting functions is at least m minus 1 to the power of cardinality E. And thus, the probability that while choosing our function at random, we bump into some good function, this probability is at least the ratio of these two guys, and this is exactly what's written down here. So let's now prove this bound on the number of good weighting functions. To prove this bound, we'll construct explicitly a good weighting function out of arbitrary weighting function that takes values only from 2 to m. So assume that for every edge, our function w maps this edge to something greater than 1. And now let's take a solution to our DLS problem with this weight function. This solution does not need to be unique, so we just taken any solution of the minimization problem. Let's call it E star. So we know that the weight of E star is equal to the minimum over all the weights of all feasible subsets. And now let's tweak our weight function so that this not necessarily unique solution becomes a unique one. Let's consider a new weighting function w hat, which is defined like this. On every element E, this weighting function is equal to the value of the old weighting function if E does not belong to E star. And it's equal to W of E minus 1 if E belongs to E star. Now, according to this new weighting function, we see that E star is kind of promoted. So if we had any other solution to the DLS problem with our original weighting function, let's name this solution as E star wave. If we look at these sets, E star and E star wave, E star cannot be contained entirely within E star wave, because then the weight of E star wave would be strictly greater. But they can have a non-empty intersection. And in this case, we see that the total decrease in the weight of elements for E star is greater than for E star wave. All the decrease in these elements is the same for these sets, but now E star contains some other elements whose weight was decreased. And thus now E star is the only winner. in the DLS problem. So now we see that E star is the unique solution to the DLS problem with the function W hat. And this transform, which we used to build W hat from the original W, is actually an injection from the set of all weighting functions that do not use 1 as a weight to some subset of good functions. Why? Well, that's because if we are given a function that was produced by this procedure, we can reconstruct the original weighting function like this. We just take our W hat, we solve the DLS problem, this DLS problem is guaranteed to have a unique solution, and then we get back to the original function by adding 1 to all the elements that happen to be in this unique solution. So this transformation is an injection. And thus, the number of all good weighting functions is not smaller than the number of good weighting functions that can be obtained according to our procedure. And our procedure is applicable to every function that does not use the minimal weight on any element of E. And the number of these functions is actually exactly equal to m-1 to the power of E. And this proves the isolating lemma.